In this video, we're going to continue with the topic of vectors, and we're going to look at collinearity today. Now, you may remember looking at collinearity before in the straight line topic, and we met a slide like this in your notes. So in order for points to lie on a straight line, i.e. points which are said to be collinear, we should observe that the gradient of the line joining two of the points is equal to the gradient of the line joining the other 2 points. And we can see in there that we had a common point as well. And as long as we had those two conditions, that then meant that the points were collinear. Now, if we change this slide slightly so that we're now not dealing with straight lines, but we're dealing with vectors. So we can see from the first diagram here that we have a common point B, but looking at the vectors AB and BC, we can see that those are not parallel because they are going in different directions. So that is not an example of collinearity. In the second diagram, we don't have any common points, but we can see that this time that the two vectors that we've been given, AB and CD, those are parallel, but because there's no common points, that's not an example of collinearity. And for the third diagram here, the one which is highlighted, we can notice that AB and BC are parallel, they're both going in the same direction, and B is a common point. So therefore, we have collinearity there. So points A, B and C are collinear if vectors AB and BC are parallel with B a common point. Okay, so it could be that A or C is your common point, that's absolutely fine, but just for this one I've made it B being the common point. Now, vectors are parallel if they are scalar multiples of the same vector, and we talked about this a few lessons ago, but I'll just clarify what that means just now as well. So we've got vector u, 8, negative 2, 0, and say we also have vector v, 16, negative 4, 0. And hopefully you've spotted by now that v is twice u. If we double u, we will get v. So v is equal to 2u, and that means that u and v are parallel because v is a scalar multiple of u. Another example, if we have A, vector A, 12, negative 3, 9, and vector V, 20, negative 5, 15. Now, I can see just now that I can't multiply A by a whole number to get B. There are obviously fractions involved here. But what I can notice is that I can express both of these in terms of the same vector, 4, negative 1, 3. Okay, so I can basically find the highest common factor of 12 and 20, negative 3 and negative 5, and 9 and 15, and get my vector from there if required. So you can see that A is the same as 3 times 4, negative 1, 3, and B is the same as 5 times 4, negative 1, 3. And because we can express these as scalar multiples of the same vector, then we can see that A and B are parallel. So let's have a look at an example involving collinearity, and we'll do 2 examples today for this. So A is the point 1, negative 2, 5, B 8, negative 5, 9, and C is the point 22, negative 11, 17. Part A asks us to show that A, B and C are collinear, and Part B asks us to find the ratio in which B divides AC. So our solution then, and I'm firstly going to show you a picture of what this looks like. So this has been plotted using 3D coordinates. Obviously we're sitting with these 3D coordinates, and we've got A, B and C here. So that's what these vectors look like. The points look like rather, and you can see I've joined the points using vectors AB and BC. Okay, so the first thing I want to do to show that A, B and C are collinear is to find the vector which joins A and B. So vector AB, remember, is position vector B minus position vector A. So that's 8, negative 5, 9, minus 1, negative 2, 5, which gives us 7, negative 3, 4. Next, we need to find the vector which joins the points B and C. So vector BC is position vector C minus position vector B. That's 22, negative 11, 17, minus 8, negative 5, 9. And that gives us 14, negative 6, 8. We now need to try and show that these are collinear. So remember, the first thing we need to do for collinearity is show that one of the vectors is a scalar multiple of the other. I can see that AB, vector AB, is twice BC. Or I can express that in a different way. AB is a half of BC. Okay, so either way is acceptable for you to express that. So AB is equal to a half of vector BC, and that means that AB and BC are parallel. Since B is a common point, that then means that AB and C are collinear. So we have proven collinearity here, and that now leaves us to do part B of the question, find the ratio in which B divides AC. So we already know that vector AB is equal to a half of vector BC. And I'm going to divide throughout here by BC to get AB over BC equals a half. And remember, we can express fractions as ratios. So that gives us the ratio AB to BC is equal to 1 to 2. And just to clarify that, if we just look here at AB, if you look at the orange arrow at the moment at the length of that, and basically 2 of these arrows should now fit into BC. So here's 1, and here's the second one. So you can see that that ratio there is 1 to 2. So just now would be a good time to pause the video, take this example down in your notes, and then come back for another similar example. Okay, welcome back folks. So example 2 then. D, E and F have coordinates 10, negative 8, negative 15, 1, negative 2, negative 3, and negative 14, 8, 17 respectively. For part A, we want to show that D, E and F are collinear, and for part B, we want to find the ratio in which E divides DF. So, like before, we've got our 3 points, and we want to find the vectors, the components of the vectors which join those points together. So firstly, DE is E minus D, and that's 1, negative 2, negative 3, minus 10, negative 8, negative 15. From there we get negative 9, 6, 12. And we now need to find the vector which joins E and F. So vector EF is position vector F minus position vector E. And that's negative 14, 8, 17, minus 1, negative 2, negative 3. That gives us negative 15, 10, 20. Now, in order to show that these are collinear, we need to show that one of the vectors is a scalar multiple of the other. Now, you might find it hard to see here what's actually happening because we can't, for instance, we can't double this vector to get this one. We can't triple it, we can't multiply it by a whole number. So what is useful to do is to take each of the components, so the first ones are negative 9 and negative 15, and one of them is 3/5 of the other. So the negative 9 is 3/5 of negative 15. Let's see if that works for the other components. 6 over 10 is 3/5. 12 over 20 is also 3/5. So what that tells us then is that DE is equal to 3/5 of EF. And that means because we can express one of the vectors as a scalar multiple of the other, that DE and EF are parallel. We also know that E here is a common point, therefore DE and F are collinear. And I should have said in the last example, in the exam and when you're answering questions in these statements are really, really important. They're communication so that you can actually say that these are collinear and why they are collinear. And it shows that you've got an understanding of what is going on there. So you need to make sure that those statements are evident in your answers. So for part B, we want to find the ratio in which E divides DF. So you can see the picture of what's going on here, okay? And we know that DE is 3/5 of EF, okay? So that means we would be able to fit 1 and a bit of these into EF. So we're going to divide throughout by EF here. So DE over EF is 3/5, and that then allows us to express those fractions as ratios. So the ratio of DE to EF is equal to 3:5. And if we just have a look at the picture of that, you can see what's going on here. So you can see that the DE is 3/5 of EF, and you can hopefully see now that the ratio in which E divides DF is 3:5. So before the screen goes blank, it would be a good idea to take these notes down in your notes booklet and then complete the assigned exercise for today.